Unfortunately, he couldn't come because of his desire, but still I'm here to present his talk. I'll do my best. So, let's go. An experience in using ADCP Rio Grande 600 kHz for investigations of the processes on the sea. So during several expedition seasons starting from 2003, TRD Instruments Europe provided Andrey Serebryany with an ADCP Workhouse Rio Grande 600 kHz. So he started his investigations in the Russian areas, Russian seas with this excellent equipment. At first, primarily it is true for measuring the intensity of the backscattered signal, and that feature allowing one to monitor different processes in the water bulk. In combination with simultaneously monitoring the background current, the ADCP becomes an exceptional instrument offering unreachable earlier possibilities in studying the processes in the coastal area. In these presentations, we're going to talk about the expeditions which were obtained by who is using ADCP from 2003 to 2017. So there were 36 marine expeditions on the shelf of Russian, Ukraine, Abkhazia, and Israel, and 30 expeditions were obtained in the Black Sea, 4 expeditions on the shelf of the Sea of Japan, an expedition on the White Sea, and an expedition on the Sea of Galilee, Lake Kinneret. So here is the map. Yes. Oh, yeah. So here we found the 3 points over here: the Black Sea, the White Sea, and the Different Sea. So for the sea observations, we used small vessel boats, yachts, as well as stationary platform. This is an example how we mounted the ADCP from the vessel. And another one picture, this is for the yacht in Gelendzhik. And this is the yacht for the observations in the area of the Sea of Japan. And this is a stationary platform. This is situated in Crimea, on the south of the Crimea coast. It is located in 600 meters from the shore, and the depth there is nearly 30 meters. And another example of ADCP mounted on the stationary platform. The good thing to measure from the stationary platform is that we can work at any weather conditions. So even during strong wind, we still have our measurements. Again, study areas of the Black Sea. You can see the Khimchenko Valley in the Crimean Peninsula here, and this is the Gelendzhik, northeast part of the Black Sea, and this is the Sukhum region, Abkhazia shelf. Study of currents on shelves of the Black Sea. So, on this map, you can see the yacht tractor with ADCP. This red lines goes. It was a survey on the 7th of October in 2015 on the northeast shelf near Gelendzhik, and here's some results of this survey. You can see a strong magnitude of the velocity here, and this is the directions of the currents which goes along shore. It is not so strong. And the study of currents in the sea at the confluence of large rivers. In the region of Abkhazia shelf, we have a strong river, Kodor River. It is right here, you can see it, and it has a great impact on the sea waters. You can see the satellite image of Sentinel-2 from the 10th of September in 2017, and here is a plume of this river waters. It goes extending to the northwest over about 20 kilometers. And here at this point, we have the stationary platform also. And we worked there at that period when we found this approaching of the plume. Here you can see the border. Approach to the shore of the hydrological front from the side of the deep sea. It was at 18th of September 2016. The sharp front delineated by foam band. Also, this front gave some interesting results. It seems that observable cones of relatively pure water. Here you can see it. Manifestation of filaments of water of the open sea, the sources of which is nearby frontal zone. So this is a backscatter recording. And here again the picture of this plume of the Kodor River. You can see this area. Here it is clearly distinguished by color. Another scheme of boat tracking during the survey with ADCP near the Kodor River. And here is in the red line, it was like a scheme, what we have to do, but in fact we made only this scheme on the black lines. Because of the shelf area here, it's really sharp. So when you go just maybe 100 meters from the coast, the depth there is much more than 100 meters. So that is why we worked only in the depth area of 60 meters, no more. And here are the results of this survey of currents in the coastal zone near the confluence of Kodor River in October 2015. And you may see that the river flow goes here, and here's a significant magnitude. And another picture of this survey of the backscattering signal, distribution of backscattering coefficient by area. So here is the area of this red lines. The confluence of river is huge. And picture of the location contrast in the section across the shelf opposite the confluence of the Kodor River above this. And the section without the river waters, so you can see how river impact could be found on the average backscattering signal. Another satellite image for this region, we show the surface manifestation of internal waves propagating to the sea from the point of confluence of the Kodor River. So not only the front, but also the internal waves would be generated of the impact of this strong river. And here is an example of internal waves in the sea at the near surface stream line with the confluence of the river Kodor according to the backscattering signal. So you might see these lines here, of course. The short period internal waves. Another part, investigation of coastal anticyclonic eddies. Another satellite image of coastal anticyclonic eddy near the region of northeastern part of the Black Sea, the Gelendzhik region, at October 2006. And here we have an eddy. These three arrows, they shows the direction in the eddy, and this red, this green arrow shows how the eddy is propagating. The eddy of 25 kilometer diameter is moving along shore to the northwest with a speed of 12 centimeters per second. And the red arrow shows the sections with ADCP when we worked them. And here is a variety of mean currents at this section, cross sections in coastal zone. Here you can find several images from 5 October to 11 October, and here is two pictures when it was an eddy at this area, and then the direction changed when the eddy passed. And here is an example of variability of intensity of currents during passing the eddy. The emergence of jets of intense flow emerging from the depth to the surface, the shear currents formed by them on the sea surface from slicks, which make it possible to observe a spiraling pattern or vortices in satellite images. At the approach of the vortex, the jet approaches the coast and the flow in them increases, as can be seen from a comparison of the records on the sections, two different sections. Above with the October 8 and below with 9. And here is the appearance of an anticyclonic vortices. So the thermocline goes up when the eddy is approaching. And to different pictures, you may see that the thermocline is over here at the 5th of October, and after the approach of the eddy, the thermocline goes up nearly 3 meters. Subsatellite measurements. Here is part of the using ADCP. It's very useful when conducting sub-satellite marine experiments. We'll continue this. Here is a fragment of high-resolution satellite image of the sea surface in 2011 in October near the region of the Black Sea shelf. And here is also the data currents measured with the ADCP during the satellite passing over this area. And here is you can see the sleek, and this sleek is coincides with the change of the directions of currents. And here is a subsatellite experiment to study internal waves in the coastal zone of the Black Sea. Again, this is the northeastern part of the Black Sea. Here's a fragment of high-resolution satellite image TerraSAR in 2012. Blue vectors denote the flow velocity and directions according to ADCP data during the satellite's flight over the water area. And the arrow indicates the surface manifestations of internal waves. And here is we have symbols AB. So this is the section. Put it to this picture. This is ADCP data for this section. Components of the currents. The top is the components of the currents. And above and below a picture of flotation patterns where internal waves nearly for 5 meter amplitude visible. And they create also the slicks on the surface. Observations of internal bores from stationary platform. Here's an example. Internal bore in the form of step of bottom cold water is apparent in the coastal zone in the Black Sea as a strong flow current in the bottom layer up to 60 centimeters per second. And these bore were observed during expedition of 2005. Here's a picture for velocity magnitude. And you can see this is this target. But here it is like a bar. So it's like a strong current which comes rapidly. Internal observations of 2005. Here is the velocity amplitude. And here is a strong subsurface current up to 80 centimeters per second. And this appearance of bore coincides with a sharp change of the velocity directions from east to west. And you can see that this is much stronger than the previous one. The study of currents and internal waves during the 80th scientific cruise on the White Sea on the research vessel Professor Stockman. This is August 2006, and this work was joined with Professor Papa and his group. The White Sea area is covered by the ADCP surface during the 18th cruise on this picture. And here's the trajectory of sections through the throat of the White Sea, this red line. Here is the ADCP mounted in streamlined body for towing for this survey. And here the ADCP towing vessel speed is about 3 meters per second. The result, the trajectory of the 55 kilometer section through the throat of the White Sea and average in depth flow in the section. This shows the variability of the direction of currents and below the change in the velocity magnitude also. Here it is. The distribution of the direction above this picture and the amplitude of the current below. You can see in depth across this throat of the White Sea. A narrow, deep hollow with a depth of 110 meters here. Is crossed in a section. Above the throat, the current maximum is not in the near surface layer, but is buried by 30 meters. So you can see here. This is a huge magnitude. And this is associated with an internal hydraulic jump over the ravine. Study of currents in the Sea of Galilee in November 2000. 2016. This work was with collaboration with Professor Katsny-san of the University of Haifa. Here is an example of vessel which they used for this expedition on Lake Kinneret. And here is a scheme of the survey during the expedition. So they went across from north to south and from east to west. And here is an example of cyclonic circulation with current velocities of from 1 to 10 centimeters per second throughout the entire depth of the lake, with direction variability within a few tens of degrees. So Professor Andrey Serebryany told me that this was the first result of the circulation at the Lake Kinneret. So previously they didn't do this. The distribution of the velocity direction in a depth on a straight section through the entire lake from south to north. So for this direction, for this section. Next, observation of internal waves. And the study area for this part is the Sea of Japan. On this picture, there is an example of slicks. Here they go to the shore. This is in the entrance of Wittas Bay. Here you may see the slicks generated by internal waves. And here is an example of manifestation of these internal waves by average backscatter signal in the Wittas Bay. How you can see it in the ADCP. Here they go. And there is an example of record of echo intensity made by Rio Grande from Enhorsiak during 20th September in 2004. And here is the internal waves. You may see them also, how they goes on the average intensity. And the pyramids are like 13 minutes, and horizontal components in orbital currents up to 0.5 meters per second. And there is a 15 meters amplitude. You may see it in the right corner here. There is an example, horizontal component of currents and vertical component of currents during passing of train of these intense internal waves on the shelf of Japan. So you see this is the north velocity, and here is the red lines, the huge velocity. Internal waves on cross sections on shelf of the Sea of Japan. This is for the 23rd of September 2004. And here is again an example of trend of internal waves registered not far from continental slope. Here is an example again. They propagate to the shore, and their heights are close to 10 meters. Another example, the pattern of backscattering signal in the top and the data of up velocity in the bottom, obtained during passing through the package of large amplitude up to 16 meters. That was recent observations in October in 2015 in Gelendzhik in the Black Sea. Oh, here's this huge internal wave is up to 16 meters height for the Black Sea. This example was the first field experimental internal waves with such a height. So 16 meters for the Black Sea for the short period of internal waves is too much. And here is a coastal front generated due to strong storm. And the passage of the front after the storm period is accompanied by a train of intense internal waves. So you may see here after the storm how the internal waves generated. And the last part, but not the least, are the important effects connected with internal waves. So here's an example. Intense internal waves in the deep part of the shelf have the form of depression waves. The left picture, this one, an example of depression. And while in the shallow shelf have form of elevation waves, they go up. And when moving to the coast, these internal waves, when they approach into the coast, they change in the polarity of the amplitudes of internal waves. So this is the scheme. This is the depression waves, and then when they approach into the shore, they became an elevation waves. Observation of shear instability in the Sea of Japan. A longshore current of 0.8 meters per second during ebb, there is a strong opposite current, 0.3 meters per second, beneath sharp thermocline. Kelvin Helmholtz instability generates train of 5 billows with heights up to 10 to 12 meters. So, this is the ebb. Horizontal asymmetry of internal waves, steepening of the frontal face. This is recording of line temperature sensor on the left, and ADCP record on the right. And train of internal solitons with predecessor record of line temperature sensors. So this one is predecessor, and then goes a huge internal wave. Effect of internal waves on subsurface layer of air bubbles in the sea. This is a modulation of thickness of the subsurface bubble layer in red color. Here it is by internal waves. So this red one is because of the air bubble. And here's an explanation of the effect due to orbital currents induced by passing internal waves. So the observed effect can be explained in terms of two mechanisms. The overturning of the surface waves that generated the undersurface bubbles in the field of convergence of the flow, and the downward current of the bubbles by the orbital flows in the internal waves. And I don't know if it's here or not, with the orbital velocities. And observations of intermafine lengths of warm and salt waters. The lengths had a characteristic horizontal size of 3 kilometers and a thickness of 4 meters in the central part. So you may see these lengths over here. And the record also reveals oscillations of lens body under the influence of internal waves passing through it. So you may find these small oscillations. Strong interaction of internal waves with the bottom. Here is a soliton-like internal waves propagating above underwater band and generating so-called dune solitons on the bottom relief. So here is the bottom of the relief. You may see that the relief looks like the internal waves which usually pass in this area. And the heights of these underwater dunes are as much as 6 meters. And finally, conclusions. ADCP Rio Grande 600 kHz provided to be a powerful instrument for studying a wide range of physical processes at a shelf. And this talk is also very important for Andrey Serebryany because this whole observations is like 15th year experience of using the ADCP in the Russian seas. So unfortunately, he could not come, but still, this is a huge work of him. Thank you.